All right, you guys, so here we are getting ready to take our AP Stats test. I have compiled, in my opinion, the top 15 most forgotten or confused things just as a last minute refresher. Maybe breeze over this the night before you take your AP exam just so that you can, put yourself in a good place and have some little tiny things to remember to avoid getting dinged for like little things. So let me know if you have any questions specifically on any of these. I'll do my best to kind of recap these top 15. Number 15, make sure you're always adding variances. This is the one and only mistake that I made on my statistics final in grad school, is that I added standard deviations together like an idiot. So remember that you can add standard deviations. Remember what we talked about in class was standard deviations, technically those are square rooted numbers. And it is bad algebra to take two different square roots and add them together. You can't do that. And so what we have to do is we have to add variances. So even if the two distributions are being subtracted, like if you're doing a situation where you have two different normal distributions, one of them represents men, one of them represents women, and you're trying to find the difference between the two distributions, even if you're subtracting, you are also always adding variances together, okay? Key word. So that is number 15. Number 14, let's talk about power. So in my opinion, there's only a few things that you need to understand about power, and it's come up a few times on these free response problems that we've been doing. But remember that you have this hoe that you are assuming to be true. But this is an incorrect center to our bell curve, and we're trying to detect that, right, by doing a test. We want to reject this because this hoe is false. And so a couple things just to refresh our memories here, that this shaded area that represents our alpha, this is the probability of a type 1 error. If we actually have a different center of our bell curve, let's call it something within the ha. Let's say that our center is actually right here. If you continue this line right here, I believe it was green in the textbook when we originally talked about this. If you continue this line that cuts off the significance level, aka the probability of a type 1 error, you continue it down here. This shaded area, which is much bigger because we have a different center of our bell curve, this shaded area represents the power, and on this side the shaded or is the type 2 probability, type 2 error. Remember, two different ways to increase your power that we talked about big time. So you either increase your sample size. The reason for that is because anytime conceptually you take a bigger sample, you gather more information about your population. Therefore, you're more likely to make an accurate conclusion, detecting a false hoe. The other thing to do is to increase your significance level. So if we increase this significance level, if I drag this line this way, this entire line also gets dragged this way, therefore increasing this shaded area as this line moves this direction. So our power also increases. The thing that came up on a free response question, maybe it was 2018 or 2017, can't remember which one. Increasing your sample size. Remember how the sample size n goes in the denominator when you're doing your standard deviation of statistic? And so essentially, if your spread is smaller, which is what happens when you increase your sample size, your standard deviation goes down. Therefore, our test statistic, the place that we actually draw our line, if this is less spread out, our test statistic where we draw our line is actually going to be farther away from the center if we have a bigger spread. So again, that makes a really small p-value, which makes us more likely to reject. All right, let's go to number 13. Big time. This is a really, really, really common mistake. But if you are doing a two-sided test, remember you have to double the p-value because you're looking at both tails if it is a two-sided test. Your calculations when you do the test statistic and the probability, whether it's a normal curve or a t-distribution, it's going to give you one of the tails. You're going to have to double that to get your p-value when you are doing a two-sided test. Number 12, condition checking. You're always checking conditions. That would be a good thing to have, like your notes packets lined up and nice and orderly and neat, so that you can make sure that you go through all your correct conditions depending on what kind of a test or an interval they might give you on the AP exam. But you're always checking conditions. if you're doing a test or an interval. And maybe, best case scenario, the directions might say you can assume conditions have been met. We've had that on tests and quizzes in our class. We've also seen it on AP problems. So if that is the case, joke's on you if you check the conditions. That's a waste of time, okay? So just read the directions really carefully, but don't forget to check the conditions. You get a ton of points for doing that whenever you're doing a test or an interval. The normal condition, so that changed a lot depending on what chapter we were looking at. So depending on the scenario, you're always checking NP and N1 minus P for proportions. Remember, if it's not a proportions problem, you don't have a P. Therefore, you can't do this NP nonsense. But for proportions, to check the normal condition, you are always checking NP and N1 minus P if you're given the P, the population proportion. Remember, we did that initially at the very beginning of second semester. We were given the proportion for the population. But as we dove deeper into statistics, we started to learn, okay, it's actually really difficult and pretty unlikely to know the proportion from the entire population. Therefore, sometimes we have a proportion that we are assuming to be true from the null hypothesis. Therefore, we're using that, the null hypothesis proportion that we're assuming to be true. If you don't have anything like that you are assuming to be true, you have to use your p hat if there's nothing else. You have to check NP hat and N1 minus P hat. In the case of doing a 2 sample or 2 proportion Z test, because Z always goes with proportions, then you're doing N times P hat 1, and also you have to do the same thing for P hat 2 if you have 2 different proportions that you're comparing. That's chapter 10 when you're doing like a 2 sample or a 2 prop test or interval, okay? And remember, what are we always checking for? They all must be greater than or equal to 10. Okay, so what about the normal condition if it's not proportions? That would mean it's means. You're looking at like an X bar or something. Scenario number 1, maybe you are told the population distribution is approximately normal. That is the best case scenario. Then you can say normal condition has already been met because you're told the population distribution itself is normal. Scenario number 2, if you're not told this anywhere in the problem, then check the CLT. Is the sample size greater than or equal to 30? If it is, awesome. That means our sampling distribution of will be approximately normal. The CLT applies. If it's not a normal distribution like a Z that you're calculating, then it might be a T distribution. And if the CLT applies, then it is safe to use T. Remember the lingo that we've discussed. Scenario number 3, that's your worst case scenario. That's when you check the modified box plot and the normal probability plot in the calculator. Sometimes they will give you these plots and you'll just have to discuss what they look like and why it's okay to proceed. But remember, in the box plot, you're looking for really, really strong, crazy looking skew. It'll probably be a little bit skewed, but you want it to not be like super crazy skewed looking. You need to also make sure that you don't have any outliers present because that will definitely throw off our calculations. And for the normal probability plot, remember that has z-scores on the y-axis. You're trying to see if that is fairly linear. Okay, so it should form a roughly straight line for the normal probability plot. Okay, number 9, expected counts. So this is for chi-squared. So we are told that chi-squared is not going to be on the 2020 AP exam. But that is the only thing that we checked to make sure everything was greater than or equal to 5. In case you were wondering, I thought I remembered something about 5. That was for chi-squared. Okay, so good news, we don't really have to worry about that. Anyways, moving on. Binomial, yes. So remember I did post a PDF of a bunch of probability practice and notes and key terms and definitions of formulas and that kind of thing. So check that out if you're still a little bit iffy on probability. But remember, binomial, how do you know if it's binomial? These are the conditions to go through to help you like think your way through. Should I do a binomial here or should I do something else? Binomial is your success failure, like win or lose, heads or tails, correct or incorrect, anything like that. That's your number 1 clue that you're going to do one of those binomial CDF calculations. Independent means each trial has to be independent from another one. That means knowing one outcome gives no info about the second outcome. You have a set number of trials. So remember, if the question tells you to keep doing something until you make 7 free throws or something like that, that means you don't know how many tries you have to do. That's a geometric situation. So just to refresh your memory, in binomial, the number of times you're doing something is defined and set. So like a 10 question multiple choice quiz, you know you have to answer 10 questions. It's not keep answering questions until ... It's you're taking 10 questions, you're shooting 53 free throws, you're flipping a coin 8 times, the set number of trials is defined. And then the last one is the S, the success probability is the same for each trial. So every single time you flip a coin, you have exactly a 50% chance of getting heads or tails. That doesn't change depending on what the previous flip was. So the success probability is the same for every trial. More probability stuff, so keeping in mind, our probability chapter was so many different strategies. It's a really corny, metaphor, but it's kind of like having a tool belt with a bunch of different tools in it. Sometimes you can try formulas, sometimes you can try a Venn diagram, sometimes you can try tree diagram, blah 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 blah. There's a lot of different strategies that we talked about in our probability chapter. That was chapter 5. If you want to take that notes packet out, you have a bunch of stuff in there. And also remember, I posted some probability review material. But here are the formulas. If you want to jot them down, you should also have them in your notes so that you can easily reference them. But the formula for and, remember, you can straight up multiply the two things together, the two events, if they're independent. But if they're not, you have to do a little bit more of a intricate formula. It has a given condition there. You can also solve for this given conditional probability by dividing both sides by probability of A, and there's your formula for the conditional one. So probability of B given A is the same as probability of A and B over A. Remember, this is kind of like a division bar, so that's how you remember that given formula. It is in here, you just have to divide the probability of A over. The OR formula, remember, you can either add them together if they are mutually exclusive / disjoint. Remember, those mean the same thing, two vocab words, mutually exclusive, disjoint. That means your two Venn diagrams do not intersect. In that case, you can just add the two events together. But if they do intersect, remember, the people in the middle of the Venn diagram got double counted. That's why you have to subtract those people away. One other important thing to remember about this independence and disjoint stuff is that two events cannot be both independent and disjoint. It could be neither, and it could be one or the other, but it cannot be both independent and disjoint, meaning two events, A and B, cannot be both independent and disjoint. Why is that? Really quickly, to refresh your memory. If they are mutually exclusive / disjoint, remember how that means that probability of A and B is 0? That means nobody falls into the intersection of the Venn diagram, right? That's what mutually exclusive means. There is nobody that falls into both categories. You can't be both a sophomore and a junior. Therefore, this is 0. And so if this is 0, this is the same thing right here. If this is 0, that means that one of these two events has to be 0. And therefore, that would be a whole different ballgame. So, cannot be both independent and disjoint. Keep that in mind. Could be neither. Cannot be both. All right, critical values. So the Z star and the T star. That is what we use for intervals. It is called the critical value, and it's on the formula sheet in the confidence interval section. You take your statistic plus or minus your critical value, which is either a Z star or a T star, times the standard deviation of the statistic. So those are the words that you're given on the formula sheet for an interval. When do you use Z star? Always for proportions, or if you know the population sigma, which this is rare, but we did do an AP problem very recently where they did give you the population sigma, and it was a means problem, but we still used a Z star. If it's a means problem and you do not know sigma, remember this is in our sentence that we write before we do any sort of a T interval or T test. We always write, and sigma is unknown, therefore we're going to use a blah 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 T test or T interval. Okay, so how do we find those? So in the calculator to find the z star, for 95% confidence, you probably already have that memorized, 1.96. But how do you find that? Inverse norm in the calculator under the distribution menu. And it's always asking you for the left tail. So if 95% is your confidence interval, that means there's 2.5% on each tail. So you have to type in the left tail and then 0 and 1. Because you're always typing in the left tail, it's going to give you a negative z. But remember, there's a plus or minus in the formula, so that minus sign is pretty much irrelevant. So inverse norm for z, inverse t for t star. And still it's going to ask you for the left tail, and then you have to type in degrees of freedom. That's what it asks you for a t. That's different for when it's asking you for a z. Okay, speaking of degrees of freedom, see how I led right into that? So for the inverse t, it's going to ask you for degrees of freedom. Oh yeah, what are all those degrees of freedom? Here we go. First of all, use n minus 1. Remember, the calculator will give you more accurate n minus 1 or degrees of freedoms, and depending on if it's a 1 sample or a 2 sample, the calculator will give you a different one. But if you're not using the calculator, remember you always use the smaller of the two populations or sample sizes, n minus 1. That comes up on multiple choice a lot, so you probably won't see that on the AP exam this year, but maybe it's called the conservative degrees of freedom. But anyway, so option number 1 is sample size minus 1. That's how you figure out your DF. And these are two different chi-squared. So if you're wondering, I remember learning something about categories. That was chi-squared. So you do number of categories minus 1 for goodness of fit. Again, we're not going to have chi-squareds on this chapter or this year's AP exam, so that's a good thing. But if you were wondering, it's blurring together in your mind, we did have a couple different of those scenarios in chi-squared. Number of rows minus 1, number of columns minus 1. We multiplied those two together for two-way chi-squareds. Again, that's not applicable here. And it's also n minus 2 for linear regression. So keep that in mind. I guess the only important thing here for DFs is n minus 1, and that's sample size minus 1. And if it's a 2 sample test, then you're taking the smaller of the two, n minus 1. Or if you're running the whole test in the calculator will give you a much more accurate, using a very complex formula that you don't have to care about right now, degrees of freedom to use. Okay, type 1 versus type 2. So remember, alpha is what type 1 is, and beta is type 2. So you can go back and rewind if you want to and go back and look at where those are on those bell curves for power. I think that was my second slide. But alpha is the type 1. Remember, a type 1 error is rejecting the null when you shouldn't. So like you actually rejected, but that was an incorrect thing to do. It was not the right thing to do. A type 2 error is when you fail to reject, but you should have. And so just keep in mind, people get really confused with these errors, but an error is doing something that you shouldn't have done. So like you rejected, but for whatever reason your sample that you gathered told you to reject, even though you shouldn't have rejected the hoe. It actually wasn't a false hoe, whatever you want to think about. Terminology here, we never, ever, ever say we accept. The two things that we do, we either reject or we fail to reject. Remember, that's the only thing that MB remembers about statistics, is anytime I bring up like, oh, we're learning how to do hypothesis tests today in stats MB, and he always points at me and goes, you never accept, Angie. You either reject or you fail to reject, you never accept. That is the one thing he remembers from statistics from when he was at Purdue. They're both errors though. So type 1 and type 2, those are both errors. Keep that in mind. It's when you do something that you shouldn't have done. Okay, going all the way back to, what was this, chapter 4, the difference between cluster and stratified. These two vocab words are really, really commonly confused. But a cluster sample, again, this is chapter 4, the cluster itself should be a small microcosm of the entire population. So for example, if I want to take like 5th period lunch, that's not the entire population of Fremd High School. But I would bet that 5th period lunch has a pretty good mix of freshmen, sophomores, juniors, seniors, guys and girls, athletes, band, theater, people who are all interested in all different kinds of things, AP students, non-AP students, I bet that my 5th period lunch, using that as a cluster, would be somewhat representative of the entire population, versus picking a stratified sample. And remember, in a cluster sample, you survey every single person in that sample. So every single person in 5th period lunch would get my survey. A stratified sample is when you divide people into homogeneous groups, so something they have in common. So for example, freshmen, sophomores, juniors, and seniors. And then taking a random sample of like 20 of each of those groups. And that makes up the sample that you're giving your survey to, or whatever it is that you're trying to learn about. So cluster samples should look like the population. It should have somehow like an even mix of all types, I'll use types in quotes, of people in it. Stratified means you have divided your population into homogeneous groups. They have something in common, and you take a few people from each of those groups. That kind of helps you make sure you get equal representation. So those are 2 vocab words that are very commonly confused. I'm guessing on the AP exam you might have to write about how would you do a cluster sample, or how would you do a stratified sample, something like that. So make sure you brush up your memory on those 2 vocab words if they choose to ask you about that. Okay, second and last thing. When you're taking a sample, remember you always take your sigma or your sample standard deviation and divide by root n. Anytime you take a sample, your standard deviation decreases. So you always put that root n in the denominator whenever you take a sample to come up with your standard deviation for your sampling distribution. Standard deviation decreases when you take a sample. So conceptually, if you think about an entire population, you have outliers on the low end and on the high end. But if you take a sample of that, chances of getting both of those outliers on the low and the high end in your sample are much smaller. So your sample is probably much less spread out than your entire population. And when you take samples over and over and over and over again, the spread is less. Therefore, your standard deviation decreases when you're sampling. How much does it decrease by? You put the root n in the denominator. Okay. And then last thing, something that a lot of people get dinged for, if it asks you anything about assigning numbers randomly, make sure you specify whether the numbers need to be unique or not. So we did examples. If you go back to chapter 5, when we did all those simulations and we were assigning people numbers, or we were letting like certain numbers represent certain people or places or things or whatever, make sure that if each number corresponds to a unique thing that cannot go into more than one group, that means that your numbers have to be unique. That means you're sampling numbers without replacement. So any different way that you feel the need to say that. We did do examples where we said like 30% of the population is sophomores or something like that. And so then you would assign the numbers 1 through 30, but since those numbers 1 through 30 don't represent specific people, it's just a percentage of the population, that's when you don't want to use unique numbers. Repeats are okay. So go back to your chapter 5, section 1 notes where we did all those simulations, and that is where you can find how to decide whether your numbers should be unique or not, but make sure you specify that, because you will get dinged if you don't specify whether you are replacing the numbers or not, whether the numbers have to be unique or not. Okay, you guys, you're ready for this. You're going to crush this thing. If you have specific questions on any of this stuff, send it to me. I hope you found this helpful. Have a great rest of your day, and good luck.